A multi-million-dollar hypercar is supposed to feel untouchable, built in isolation, engineered beyond comparison, sealed off from anything ordinary. But that illusion cracked the moment Mat Armstrong began stripping down a crashed Bugatti Chiron on camera and exposed the million-dollar Volkswagen parts inside. This is one story you just can't skip. Let's start from the very beginning. The car at the center of the controversy was not an ordinary Chiron. It was a Bugatti Chiron Per Sport, one of only around 60 ever produced. Built during Volkswagen Group's Bugatti era, the Per Sport represented a more aggressive evolution of the already extreme Chiron platform. Its 8-liter quad-turbocharged W16 produced roughly 1,500 horsepower, but outright speed was no longer the sole focus. Bugatti reworked the gearing, suspension, aerodynamics, and weight distribution to make the car sharper, more responsive, and more capable through corners. At over $3.5 million before customization, the Per Sport existed in a category where engineering excess itself became part of the product. One of those cars belonged to Florida-based influencer Alex Gonzalez, known online as FXLXG. By 2024, the car had become a recognizable fixture across social media, appearing in videos, online content, and public events. But hypercars attract attention in both directions. The same visibility that amplifies status also magnifies failure. The crash itself was surprisingly mundane. There was no racetrack spin, no triple-digit highway run, no dramatic loss of control. Traffic slowed unexpectedly. Braking cascaded forward. The chain reaction ended with the Per Sport taking a violent impact. Despite being rear-ended, the Bugatti's front structure absorbed catastrophic damage. Carbon fiber bodywork shattered apart, aerodynamic channels collapsed, suspension geometry was disrupted, and critical front-end systems were compromised instantly. The headlights alone represented an enormous financial hit, while deployed airbags confirmed the incident had escalated far beyond cosmetic damage. A Bugatti technician was flown in from Europe to inspect the car directly. The assessment followed the same logic used throughout the high-end insurance world. Once repair costs approach or exceed critical value thresholds, even ultra-rare vehicles can be declared economically impractical to restore. The Per Sport's rarity did not protect it from that outcome. The car was officially written off and sent into the salvage system, eventually landing at Copart, where damaged exotic vehicles are auctioned. That could have been the end of the story. Instead, Gonzalez bought the wrecked car back himself after the insurance settlement. Reports place the repurchase cost around $1.6 million before additional auction fees pushed the total even higher. On paper, the decision seemed irrational. He had effectively spent millions recovering a destroyed hypercar that most of the industry considered financially hopeless. The project changed entirely once Mat Armstrong became involved. Armstrong had already built an audience around rebuilding heavily damaged performance cars, but a Chiron Per Sport operated on a completely different level. This was not a crash sports car with replaceable panels. The Bugatti used an advanced carbon fiber monocoque structure built around microscopic tolerances, extreme cooling requirements, and one of the most complex drivetrains ever installed in a road car. The damage extended deep into the vehicle's core architecture. Front structural sections were compromised, lighting systems destroyed, mounting points distorted, and concerns emerged around the integrity of the carbon fiber tub itself. In a hypercar like the Chiron, the monocoque is the car. Every major component attaches to it. If that structure is compromised beyond acceptable tolerances, the repair moves beyond traditional bodywork into the realm of high-level engineering reconstruction. For many observers, the conclusion seemed obvious. The car was finished. Bugatti's own ecosystem reinforced that perception. The company's servicing structure is built around tightly controlled repairs, specialized facilities, and factory-approved procedures. Outside that network, restoring a heavily damaged Chiron Per Sport was viewed as unrealistic at best. Then Armstrong began taking the car apart piece by piece. But it wasn't going to be easy. Once the rebuild began, the biggest obstacle was no longer the crash damage itself. It was access. Bugatti refused to support the restoration and would not provide official replacement parts through its normal channels. In the hypercar world, that changes everything. Cars like the Bugatti Chiron per Sport do not operate within an open aftermarket ecosystem where components can simply be ordered on demand. Nearly every major part flows through tightly controlled manufacturer networks tied directly to the car's VIN. That VIN became the center of the dispute. According to details discussed throughout the rebuild process, the car's identification status had effectively been restricted inside Bugatti's internal system. Once that happens, authorized dealers cannot freely process parts requests or perform standard factory-back servicing. The car still physically exists, but within the manufacturer's infrastructure, it is treated differently. The normal restoration path, involving dealer access, factory ordering, approved repairs, and manufacturer oversight, effectively disappears. The rebuild was suddenly operating outside the official ecosystem entirely. You see, the Chiron is not built like a conventional car. Its carbon fiber monocoque forms the foundation of the entire vehicle, integrating structural rigidity, suspension geometry, crash protection, and drivetrain alignment into a single core shell. Repairs involving that structure are extraordinarily sensitive. Even small deviations can affect aerodynamics, chassis balance, high-speed stability, and stress distribution throughout the vehicle. Publicly, resistance to the project was reinforced by Mat Armstrong, who questioned whether a rebuild of this scale could realistically meet factory-level standards outside Bugatti-controlled facilities. His position centered on engineering precision and safety. A Chiron capable of nearly 300 miles per hour is not something manufacturers want reconstructed through improvisation. From Bugatti's perspective, procedures involving chassis separation, monocoque inspection, and structural realignment require calibrated equipment, dedicated jigs, factory measurements, and technicians specifically trained within Bugatti's own environment in Molsheim, France. Even microscopic alignment discrepancies could theoretically become dangerous at extreme speeds, but the rebuild team approached the car differently. To them, the Chiron was still a machine, an extraordinarily complex one, but not an untouchable object beyond repair. Instead of relying on factory channels, they began sourcing alternatives independently, fabricating damaged sections, reverse engineering solutions, and rebuilding systems piece by piece outside the manufacturer's framework. That clash transformed the project into something much larger than a salvage rebuild. It became a public argument over ownership itself. How much control should a manufacturer retain once a customer legally owns the vehicle? Can a company effectively lock a multi-million-dollar car out of its own support network after a major accident? And if skilled engineers can restore the vehicle independently, who ultimately decides whether the repair is legitimate? This dispute unfolded publicly across millions of views online. While this was happening, Armstrong refused to give up. The Miami workshop that received the wrecked Bugatti Chiron per Sport was never intended to handle factory-level hypercar reconstruction. There were no OEM fixtures, no manufacturer jigs, and no direct technical pipeline from Bugatti. What began there was not a conventional repair, but a parallel engineering system built from scratch. With official support effectively unavailable, the rebuild shifted from replacement-based servicing to full-scale reconstruction. In a normal environment, hypercars rely on controlled manufacturer supply chains for structural, drivetrain, and electronic components. Here, that chain was absent. The only option was to recreate missing functionality through a mix of sourcing, reverse engineering, and fabrication. The foundation of this approach was digital reconstruction. Damaged components were scanned in high resolution to generate accurate 3D models. These models replaced traditional factory diagrams and became the basis for machining new parts. Computer numerical control manufacturing then translated those digital files into physical components with tolerances tight enough to match high-performance automotive requirements. Techniques of this kind are common in aerospace and elite motorsport engineering, where original parts may be unavailable, and precision cannot be compromised. One of the most significant operations was the structural separation of the vehicle. The chassis was split to access internal assemblies, including drivetrain mounting points and transmission housing areas that had absorbed major crash forces. This is not standard practice in most automotive workshops, even at the supercar level. The split exposed the car's internal architecture, revealing how deeply integrated the Chiron systems are within its carbon fiber monocoque. Once exposed, the engineering problem became more than cosmetic restoration. The gearbox mounting structure, which governs alignment between engine, transmission, and chassis, required a detailed assessment. Any distortion in this area affects not only drivability, but long-term mechanical stress distribution and stability at extreme speeds. Rather than replacing entire factory assemblies, the team moved towards structural rehabilitation. Load paths were analyzed, damaged sections were reinforced, and geometry was carefully restored to preserve original alignment. The objective was not simply to replace parts, but to recover functional integrity within the constraints of the original design. Where factory components were inaccessible, custom fabrication became essential. The cooling system was a clear example. Multiple radiators had been destroyed in the crash, yet the Chiron's performance depends on extreme thermal efficiency. Instead of waiting for official supply channels, replacement units were engineered and built to match required performance specifications, prioritizing function over branding or factory origin. Interior and safety systems required similar adaptation. Certain components, including airbags and trim elements, were substituted where original parts could not be sourced under restricted conditions. The interior was rebuilt to restore its original layout and appearance. Even when some underlying components originated outside manufacturer supply channels, the focus remained on functional restoration of the cabin environment rather than strict OEM replication. Then there was the electronic architecture. Modern hypercars operate through tightly integrated control systems where multiple electronic control units communicate across drivetrain, safety, and performance subsystems. Any deviation in components risks system-wide malfunction. Rebuilt and substituted parts had to be calibrated so that they could communicate correctly within the existing network, preserving operational coherence across the vehicle. At every stage, the guiding principle shifted away from part replacement and toward functional equivalence. Instead of asking what factory component fits a given location, the engineering question became what function the system must perform, and how that function could be reconstructed under non-factory constraints. The most critical phase was the reassembly of the carbon fiber monocoque. Once repaired and reinforced, the two halves of the chassis had to be realigned with extreme precision. Even minor deviations in geometry would affect suspension behavior, drivetrain alignment, and stability at high speed. The process required repeated measurement, adjustment, and verification. Only then would the structure be brought back within acceptable tolerances. By the end of this phase, the vehicle was no longer a factory-assembled hypercar, but neither was it a static wreck. It existed as a reconstructed system composed of original Bugatti components, repaired structural elements, and newly fabricated parts integrated into a single working machine. The rebuild demonstrated a broader technical reality with sufficient expertise in digital modeling, CNC fabrication, structural repair, and systems integration. Even highly complex hypercars can be reconstructed outside manufacturer ecosystems. It also showed how modern automotive engineering increasingly overlaps with aerospace-level methodologies, where physical parts are often just the final expression of a digitally engineered process. Mat Armstrong and his team effectively proved that the boundary between factory-only repair and independent reconstruction is less absolute than traditionally assumed, even for a machine as tightly controlled